Let's take a look at some vector operations. To add vectors v and w, you would do the following. First, you would draw vector v. Now I've already done that for you in the upper right-hand corner. Let me just go over it in red to make it clear which is vector v. Then, from the terminal point of v, so from the terminal point of v, you will connect the initial point of vector w. So let me show you what that's going to look like. Vector w connects to vector v, and we can see that vector w begins with that initial point and is connected to vector v with its terminal point. The sum of these vectors is the vector whose initial point coincides with the initial point of v and whose terminal point coincides with the terminal point of w. Now, what that means is once you have connected vector v to vector w, you're going to go back to where you started, which was my initial point of v, and I'm going to connect that to the terminal point of vector w, and that vector that I've drawn in blue is what is represented as the sum of the two vectors. Now, does vector addition have the same properties as regular addition? In order to answer that question, we're going to take a look at a word problem. Example 1 says, Jessica leaves her home and walks 2 miles due east and then 5 miles southwest. Part A, illustrate this situation assuming that the direction of southwest is a 45-degree angle. Part B, although Jessica has walked 7 miles, a faster route would be to take the direct route, walking diagonal. Use a trigonometric law to find the length of this faster route. Part C, what if Jessica left her home and walked 5 miles southwest and then 2 miles due east? Would she arrive in the same location? And then based off of all of these observations, what can we say about vector addition? So now let's take the time to answer each one of these questions one by one. So we'll begin with Jessica leaving her home and walking 2 miles east and then 5 miles southwest. And part A asks us to illustrate the situation. I always like to draw an illustration using the rectangular coordinate plane because it's nice when we're dealing with direction, because what we know as my vertical axis can also be called my north-south, and what we know as my horizontal axis can also be called west and east. All right, so let's see here. Starting at the origin, Jessica is leaving her home, so I'm going to call the origin her home. And she's going to walk 2 miles east, so I'm going to put a vector that is headed east, and because I'm going 2 miles, that vector has a length of 2. Notice on here that this thing has not only direction but magnitude. The direction is east, the magnitude is 2. That's the length of the vector. And then from that point, I'm going to connect to that 5 miles southwest. And it says that we can assume that southwest is a 45-degree angle. So from the terminal side of the original vector, I am going to put onto that a vector that goes south and then 45 degrees. And I'm just going to estimate this. I know that it's 5 miles, so it should be longer than the 2-mile vector, and it looks something like that. Part B, although Jessica has walked 7 miles total, a faster route would be to take the direct route. In other words, walking the diagonal. Let's see where that diagonal is. That diagonal would be right here. Let me just dot that, and I used green, which you can't see very well, so let me go over that. It says use a trigonometric law to find the length of this faster route. Let me call that faster route, how about if I call it C? And what I want to do in order to find that value of C is identify some of the things that I know. And it appears that I know two lengths, and I'm trying to find the third. And it looks like I also know, because I turned 45 degrees, that the angle between the two vectors is a 45-degree angle. So I'm being given a side. I also know an angle, and then I know a side. So that should sound familiar to you the way that I just said that. It looks like what we have is a side angle side triangle. And so we know from previous lessons that we can use the law of cosines. So I'm going to say that c to the second power is equal to 5 to the second power plus 2 to the second power minus 2 times 5 times 2 times the cosine of the angle across from C, which is 45 degrees. Now, you can go ahead and put this entire right-hand side into your calculator, or you can try to do it on your own. These numbers shouldn't be too bad. And then you're going to get something for C squared, and then you're going to take the square root. I'm going to go over this. I'm just going to tell you what the answer is, because we certainly have worked a lot of these in previous lessons. I came up with approximately 3.85 miles. So certainly taking the diagonal is saving Jessica quite a bit of distance. Instead of 7 miles, she would be walking 3.85 miles. Part C. What if Jessica left her home, and instead of going 2 miles east and then 5 miles southwest, what if instead she reversed it and she went 5 miles southwest and then 2 miles due east? Would she end up in the same location? All right, so starting at home, which was our origin, now she's going 45 degrees southwest. So I'm just going to cut that quadrant in half. There's 5. And now she is going to go to east. And it looks like she does, especially if my graph was a little bit more accurate, she does end up in the same location, which I've indicated with that green circle. So based off of this observation, what can we say about vector addition? In other words, do you remember what the rule is, where if you take two numbers, and you add them, and then you switch the direction, the equality remains? Something like 2 plus 3 we know is equal to 3 plus 2. And that rule is the commutative property. So what we just found out with this example is, just like with addition, where the commutative property is true, for vector addition it works as well. That means that vector v plus w, if that's what I called these, would be equal to vector w plus vector v. On the next slide, we're going to summarize some of the other properties of vectors. All right, so on this slide, we have everything all at once. Let's just take this step by step. We just talked about Jessica's trip and used that as evidence that vector addition is commutative. So even though we already said that, let's just summarize it on this slide. That is, if vector v and w are any two vectors, then we know that the order in which I add them can change and not make a difference to the equality. Some of the other properties of vectors are that vector addition is associative. That is, if we have three vectors, u, v, and w, then if we have vector u plus vector v plus vector w, where v and w are being grouped, we can put them in the same order, but just change the grouping and the equality stays. That's what the associative property says. The zero vector has the property that if you take any vector and you add 0 to it, of course by the commutative property, 0 plus that vector is going to equal vector v. And if vector v is a vector, then negative v is a vector of the same magnitude, has the same length, but that negative on the front of the vector makes it go in the opposite direction. Now that's going to come in handy for us in just a little bit when we talk about subtraction. So here's what we can say. Vector v plus the opposite of vector v is going to put me back to where I started, or in this case, 0. And this is going to allow us to write the difference of two vectors. Instead of writing vector v minus vector w, we could say that vector v minus vector w is the same thing as vector v plus the opposite of vector w. Now, there's a whole set of rules for subtracting vectors, but the way I'm going to deal with it in this class is just to always refer it back to addition, because that way we only have to remember one thing. Now let's take a look at one more grouping of vector operations. Specifically, we're going to talk about multiplication. So our definition is if alpha is a scalar or a real number. So in other words, what I just said there is that if I use the terminology scalar, all that I'm really talking about is a real number. And v is a vector, then the scalar product indicated by the multiplication of alpha and v is defined as follows. If the scalar is greater than 0, then the product of alpha and v is the vector whose magnitude is alpha times the magnitude of v and whose direction is the same as the original vector. In other words, by multiplying some vector by a real number, let's say 2, my new vector is going to be in the same direction, but just twice as long. Number 2, if the scalar is less than 0, so it's a negative number, then the vector is going to have the absolute value magnitude times the magnitude of v, and whose direction is the opposite. So on the previous slide we talked about what putting a negative does. It just moves the vector in the opposite direction. So if we had, let's say, negative 2, the vector would still be twice as long, but it would be twice as long in the opposite direction. And then finally the third one, if the scalar is equal to 0, or if v equals 0, then we can say that alpha times vector v is equal to 0. Now let's take a look at an example to try and have this make a little bit of sense. Example 2 says use the vectors that are given to graph each of the following vectors. And I've given you in the picture vector v, vector w, and vector u, and I'm asking you to find 3 things. The first thing I'm asking you to find using the picture is what is vector v plus vector w. Now what I mean by that is I want to see that vector. So what I learned on a couple slides ago is that in order to add 2 vectors from the terminal side of the first vector, which is v, so there's my terminal side of v, I need to connect to that the initial side of w. So this initial side of w needs to get scooted over and connected. So I'm going to go ahead and do that in order to make sure that the direction and the magnitude of w remain unchanged. I'm going to notice that vector w, where it starts and where it ends, are 2 to the right and 2 down. So from the terminal point of v, I'm going to go 2 to the right and 2 down and connect those and know that what I've just done is perfectly moved vector w. Now I'm not quite done, so make sure that you don't ever stop there. We have connected v and we have connected w, but the question now is, okay, well, where is vector v plus vector w? And the answer is that now I'm going to connect those 2 vectors, starting with the initial point of the first vector and then showing my direction by where it ends. So that vector in blue is what I would indicate is vector v plus vector w. All right, now the next one, 2 times vector v plus vector w. So you might even be able to visualize this. If you imagine vector v getting twice as long, and then that vector w that I put in green is just going to scoot up with it, then 2 times vector v plus vector w is just going to be the vector that connects the two of them. I'm going to put up some new graph paper here so that I can transfer all that over. It's starting to get a little bit messy. So let me go ahead and reproduce vector v. Vector v looks to me like where it starts and where it ends is a movement of 1, 2, and 3 to the right, and then moves up 2. So let me start on this bottom corner on my graph paper, and I'm just going to roughly sketch 1, 2, 3 to the right, 3 to the right, and then up 2, and I can say, okay, well that's vector v. But remember, I'm multiplying that by 2, so I've got to do it again. I'm going to go 1, 2, 3 to the right, and I'm going to go up 2. So those two vectors represent 2 times vector v. Now, from the terminal point of this new vector, I'm going to connect the initial point of vector w. And if you remember what vector w does, it goes 2 to the right, it goes 2 to the right, and then it goes 2 down. So I'm going to connect, and that is vector w. That didn't change. But what did change is from where I started to where I end, that is my new vector called 2 times vector v plus vector w. So you have to connect them, you have to make sure that you have the direction indicated, and then you want to label what that vector is. Also note on this one that the 2 that's in front of the vector is what we call the scalar. All right, and finally one last one. We have vector v plus 2 times vector w minus vector u. And I think in order to get a good picture, I'm going to clear my screen so that I can have a new piece of graph paper with just part C on it. So I'm going to erase this. There it goes. And let's see, I'm going to go ahead and recreate vector v, which I know is 3 to the right. And let's see, 3 to the right, 1, 2, 3, and up 2. So there is vector v. And then remember, vector w was 2 to the right and 2 down, 2 to the right and 2 down. But then I need to do that again, 2 to the right and 2 down. And I think I should have started my graph up higher, but that's all right. This is going to be 2. And actually, you know what? I think I'm going to erase this so that I can, yeah, I'm going to have to erase this because I'm looking at you. I'm going to run out of room. So this happens a lot. Sometimes you start in the wrong spot and you just have to erase. Let me start again. I'm going to start up a little bit higher. You have to erase once you start seeing where things are going to go. So I'm going to start up higher, and I'm going to start over with vector v. So vector v is 1, 2, 3, and up 2. There's vector v. So from that terminal point, now I'm going to add 2 of my vector w's. So 2 by 2 and 2 by 2. That's what vector w is. So there's 2 of them. All right, and then minus u. So this is the new part. Instead of writing minus u, I am going to rewrite this problem as plus the opposite of vector u. So normally what vector u does is I'm going to do this in a different color. Normally what vector u would do is it would go 1 to the right and then up 1, 2, and 3. So normally I would say 1 to the right and up 1, 2, and 3. So that's maybe what adding u would look like. I'm going to do just the opposite. So my vector is, instead of going 1 to the right, it's going to go 1 to the left, and instead of going up 3, it's going to go down 1, 2, and 3. And that is negative vector u. So that's me taking subtraction and rewriting it as an addition problem. And now if I connect where I started to where I ended, and I don't have a ruler, so this isn't going to be perfectly straight, but it'll look something like that. That's what would be represented by vector v plus 2 times vector w minus vector u. On this slide, we're going to make some observations about what we just did on the previous slide. On the previous slide, in order to re-sketch the vectors onto your own graph paper, you had to determine the horizontal and the vertical movement to get from point to point. So let's try to remember what we did on that last slide, and you may need to pause and go back a slide. I'm going to let you do most of this and then just double check with what I put here. I say, for example, in vector v, we said to get from the initial point to the terminal point required us to move 3 horizontal units and 2 vertical movements. What you did was you found an algebraic way of representing vectors called components. Okay, so maybe pause this video and go back and pay attention to how I redrew vector v. I had an initial point, and then I said, well, to get to the terminal point, I have to go to the right 3 and then up 2. Another way of saying that is to say that vector v is equal to 3, 2, and the component notation are these little symbols that look like V's on their sides. Based off of this, use components to express vector w and vector u. Now, again, you should pause the video and make sure that you're able to do this. Let me go ahead and just talk it through, assuming you have paused. What I said on the previous slide was that to get from the initial point of vector w to the terminal point of vector w, I had to go 2 to the right and I had to go 2 down. And so that would be represented in component form as 2, -2. These are not parentheses. If they were parentheses, it would look like an ordered pair. This tells me the component form, which is the movement, horizontal and vertical. For vector u, I had to move 1 to the right, and I had to move 3 up, so that becomes 1 and 3. So now here comes the interesting part. Go back and look at your graph of vector v plus vector w, and look at the position of the final vector. In other words, the one that I drew in. Starting at the origin, where we started with vector v, and then where we ended, count the horizontal and the vertical movement. Now, when I do that, I came up with 5, 0. So again, I'm not talking about vector v, I'm not talking about vector w, I'm talking about the new vector that we drew in. From where I started to where I ended, I would have to move 5 to the right and go nowhere up and down. And that puts me at 5, 0. So my question is there a connection between vector v, vector w, and what did we say vector w is? We said, so let me circle this, vector v, which is the 3, 2, and vector w, which I said is 2, -2, and vector v plus w, which I've said is 5, 0. Is there a connection between all of those numbers? Well, I hope that what you're seeing is that if I take the first part of the component, the 3, and I add it to the first component of the w, which is 2, 3 plus 2 sure enough is 5. And if I take 2 plus negative 2, sure enough, I get 0. So I can graphically do it just by using my properties of adding vectors, terminal points to initial points, but by writing it in component form, I maybe have a little bit more of a direct route. So what I'd like you to do at this point is go back to the previous slide and check your work. Check the answers that you got for the component form with the answers that you got on the graph. Now I'm going to go ahead and work through this real quick for you. If I take a look at the part B, which was 2 vector v plus vector w, so this was part B, and I look at what that new vector looked like on my graph. In other words, I'm not looking at my picture for 2 times vector v. I'm not looking at my picture for vector w. I'm looking for the new vector that I drew in. And from the initial point to the terminal point, if I count movement to the right and movement up, I come up with 8, 2. Now, let's think about this. The algebraic way of doing this problem would be to take 2 times vector v, which I now know is 3, 2, and adding it to vector w, which I now know is 2, negative 2, and I think you're going to like this. 2 times vector v can be rewritten as 6, 4, because 2 times 3 is 6 and 2 times 2 is 4. And if I add that to 2, negative 2, do I get what I saw on the graph? And I think the answer is yes. 6 plus 2 is 8, and 4 plus negative 2 is 2. So that checks. And then let's do the third one. The third one was vector v plus 2 times vector w minus vector u. So again, I'm not looking at the individual vectors. I want you to go back to the previous slide and look at where you started and look at where you ended and count horizontal movement and vertical movement. Where do you end up on the graph? And what I got when I did that was horizontal movement of 6 and vertical movement of down 5. Now let's see if algebraically that works. Vector v, I'll just put a line here to keep these separate. Vector v is 3, 2. And if I take 2 times vector w, let me see if I can just do this one directly. 2 times vector w, here's vector w. So 2 times 2 is 4, and 2 times negative 2 is negative 4. And then I'm going to subtract vector u, and vector u is 1, 3. All right, so for my first part of the component, what is 3 plus 4, which is 7, minus 1? And sure enough, that is 6. And then what is 2 plus negative 4, that's negative 2, and negative 2 minus 3 is negative 5, and so it checks. So the answer from the previous slide is yes, there is a connection, and we can easily see that connection if we position the initial point of the first vector at the origin of the rectangular coordinate system. And if we do that, in this case, the vector is called our position vector. Now let me show you a picture of that. So if you take a look at this picture, all of these vectors are equivalent. They have the same direction and they have the same magnitude. but the one that starts at the origin is our position vector. And it's a nice place to be because wherever I end up on my XY axis, in other words, whatever that point is, will define the components of my vector. For example, the vector that's up in the second quadrant, if I were to move to the left and move up, what that ordered pair is would not represent my component form. It would not represent my horizontal and vertical movement like the position vector does. So we're always going to try and position things at the origin so that we're dealing with the position vector. So here's a big definition for you. An algebraic vector is represented as v equals a comma b, where a and b are real numbers, or called scalars, and they're called the components of the vector. If the vector's initial point is at the origin, or 0, 0, and the terminal point is at AB, then vector v is called a position vector. A position vector describes the horizontal and the vertical movement of the directed line segment from the initial point.